Let's get started. The first topic for today is about this stability, this constant adaptation gain parameter adaptation algorithm. And our goal is to prove as long as you follow this parameter adaptation, you will be guaranteed that the adaptation error will not blow up. All right. The steps are as follows. Step one, we already transformed these two equations about theta hat and epsilon to these set of equations that are related to the difference between the true parameter vector and the estimated parameter vector, which we denote as theta tilde. And we worked out this equivalent block diagram where this linear time invariant block is simply 1. And then the nonlinear block is characterized in this way. Where we ended up last time was the fact that the bottom block actually can be shown to satisfy this Popov inequality. In other words, it is passive. And the approach that we did was by observing the fact that epsilon is related to theta tilde. And then we added and subtracted this quadratic term about theta tilde k. And we ended up here from last time. Okay. Our observation was the fact that this one has a quadratic term about theta tilde k plus 1, a cross product term between theta tilde k plus 1 and theta tilde k, and then finally a new quadratic term about theta tilde k. So this is essentially a square term. This is essentially f to the power of 1/2 times theta tilde k plus 1 minus f, this matrix taking the square root in a sense, then times theta tilde k, this transpose times itself. That's the purpose of completing the squares. And we know from this, we know that this is always non-negative. It's a vector. Check the dimensions. Matrix times a vector. This is still a vector. So this is a vector transpose times itself. Its dimensions are, this is a row vector, this is a column vector, and it's always positive, or at least 0. That's the key for completing the squares. And the remaining term over here, this is also structurally very nice in the sense that this equals, if you write out the specific terms in this summation, you will notice that this is theta tilde k plus 1 transpose f inverse theta tilde k plus 1. This is K1. So in the end, K is K1. I'm going to write out the summation form term by term, or at least the beginning terms. This is minus theta tilde K1 transpose F inverse theta tilde K1. That's the when K equals K1. When K equals K1 minus 1 in the summation, we are going to have plus theta tilde K1 minus 1 plus 1, right? This is this term when K equal to K1 minus 1 times F inverse times theta tilde K1. So these negative 1 and 1 will cancel with each other. Minus theta tilde K1 minus 1 F inverse theta tilde K1 minus 1. This is when K equal to K1 minus 1. This two term will become these two. You can continue the exercise and notice very quickly that a lot of cancellation will happen. The only thing that's going to remain, or everything in between the start and the end will cancel. This is negative theta tilde K1. This is positive theta tilde K1. So they will cancel with each other. Similarly for this term and whatever that comes afterwards in here. And the only thing that remains is when you write out the last one, this is theta tilde, when K equal to 0. At the beginning, it's going to be 1 F inverse theta tilde 1 minus theta tilde 0 transpose F inverse theta tilde 0. And everything will cancel out up to here. The only thing that's going to remain are this term and this term. So it is a big summation, but in the end, it's actually just two terms. So looking at this result, we will see again, this is again a scalar, right? We have column vector transpose. This is a row vector times a matrix times another column vector. This is a scalar. Everything is a scalar. So it's going to be larger than or equal to negative 1/2 theta tilde transpose 0 F inverse theta tilde 0. Because this first term is always non-negative. So we have a larger than or equal to sign. And everything we have accounted for now, right? We have accounted for this big chunk. We have also accounted for this big chunk. So the entire left-hand side is going to be at least larger than or equal to negative 1/2 theta tilde transpose 0 F inverse theta tilde 0. And we can take gamma 0 squared to be this theta tilde transpose 0 F inverse theta tilde 0. That's how we have obtained a lower bound for this nonlinear feedback block. Any questions for here? So now we have shown that this is passive. It satisfies the Popov inequality. And the next step is quite obvious for this case. We need to show that LTI block is strictly positive real, which is indeed the case. A positive constant is strictly positive real. So that is indeed true. Okay. So from the first three steps, from step 1 to 3, we have essentially concluded that the PAA is asymptotically hyperstable. All right. So that means asymptotic hyperstability will conclude that this error, this epsilon, which is essentially the state, which is essentially the input as well as the output of this LTI block, will be bounded. All right. So the last remaining thing to check is that the W signal is this W signal here. Actually, I would call, yeah, this W signal here. W is bounded. Then we will have conclusion that epsilon k plus 1 will converge to 0. This is a subtle thing in hyperstability theorem. If you go back to the definition of hyperstability, this is one of the criteria inside. We need to assure that the W signal is bounded. All right, so the signal that comes out of this nonlinear block is bounded and satisfy the Popov inequality. Then we can confirm that the adaptation error will converge to 0. Okay. So to see that this is bounded is actually quite obvious from this block. So usually we want to see this is bounded after by treating this signal as the output of the nonlinear block. But that path is non-trivial. It is not so easy to see that the signal coming out of this big chunk of nonlinear update will become bounded. However, for this particular case, you can see that W, this is negative W going into the LTI block. And if this LTI block is a stable, asymptotically stable transfer function, all the poles are inside the unit circle, then if the output is bounded, the input must also be bounded. All right. And in this case, actually, it's obvious. You see, the output is equal to negative W. So if we know epsilon k plus 1 is bounded, then obviously W is also going to be bounded. All right. So epsilon k plus 1 equal to negative WK is bounded. Therefore, WK is bounded. So therefore, indeed, the adaptation error will converge to 0. That completes the parameter adaptation, constant gain parameter adaptation algorithm stability analysis. All right. So essentially 3 steps follow this recipe. First, transform it into a nonlinear, into a feedback connection, and then show passivity of the feedback block, as well as the strictly positive realness for the LTI block. Then finish up with showing that the signal here is a bounded signal. Then we can have the error converging to 0 condition. That is the stability analysis. Now, you may wonder, you may still see some thing that's not clear at this stage. We have shown that this goes to 0, but can we immediately say that the adaptation estimate, the parameter estimate, will go to the true value? Theta hat will go to theta. All right. So in other words, can we guarantee convergence? This is a convergence question. This is a stability question. Can we guarantee convergence from stability? Right? The answer is not really. From the analysis, what we only know so far, right, is we can see it also here. Epsilon k plus 1 equal to negative theta tilde transpose k plus 1 times phi k. So epsilon going to 0 does not mean theta tilde will go to 0. Because this is a product between two vectors. The result going to 0 does not mean these two individuals are 0, or at least the theta tilde is 0, right? Because these two vectors can be perpendicular to each other. And in that case, none of them needs to be 0 to generate a 0 output. All right, so it is not true to claim that we will have guaranteed parameter convergence. That's why that needs to be separately treated. So we have concluded that this signal will go to 0. And this fact cannot guarantee that we will have the parameter converging to the true value. In other words, this signal going to 0 does not guarantee that theta tilde is 0. Because these two vectors, if they are perpendicular to each other, the product will be 0. So this is not necessarily 0. Okay? So that is the recipe of PAA stability analysis. We will use this recipe again over the next few lectures to talk about the general case when this LTI block is no longer 1. It's not as simple as this. It can have it can be other transfer functions. We'll talk about that, those general cases next time. A few more remaining, some small tips and exercises is what I would like to go next. We have what we know so far. In a nutshell, is passivity and strict passivity. Can lead to stability, right? If it's strictly passive, energy decreases to 0, then that means all the states must go to 0. And then what we also know is this concept of passivity can be expressed in two directions. For linear time invariant systems, passivity is characterized, it's equivalent to positive realness. Right? And then for nonlinear systems, passivity relates to is judged by the Popov inequality. All right. And with these and the fact that interconnected passive systems are passive, we can have these beneficial results of stability. All right. So a feedback connection of two passive systems will be passive. That's very helpful. Let's take these facts into some exercises. I would like to work on a few examples where scenes will include integration of signals, will include, let's say, interconnection of two blocks where h of x is in this h of x is a static function. It takes the input x and it generates a number. And what can be said is that this number will be bounded in a region. All right, so it can have variations of the output. So it's not a linear time invariant system, but we're going to consider whether this new connection of two systems will be passive or not. Let's take a look. So the first one is integration. So we can have there are two approaches. The first perspective is to recognize that integration is equivalent to 1 over s in Laplace domain. And for this one, we can check that integration, it is actually positive real. This transfer function is positive real. There are a few conditions, right? This transfer function cannot have unstable poles, which is true. It can have marginally stable poles, but for the marginally stable poles, the residual, it cannot repeat. We cannot have double roots at the same location on the imaginary axis. And for the marginary pole, we must also have the residual, which is the coefficient over here, which is 1. The residual is positive, which is also true in here, right? And lastly is the real part of the frequency response, which is the real part of the 1j omega, right? This one has to be non-negative. And that is also true in here. This complex number is always on the imaginary axis. So it is always non-negative. That is from the approach of, we treat this as a linear time invariant block. We can also use definition in here and consider the integration between the input and output So what we can notice is that if you integrate u to generate y, then the relationship is that u is the derivative of y. That's how, if this is the derivative, if this is y dot, you integrate it, you get y. So this cross product between u and y and integration, it is really nothing but integration of y dy, which is half of y squared t1 minus half of y squared at initial time 0. And then this is going to be larger than or equal to 1/2 of y0 squared. So lower bounded by some negative number, for sure. That depends only on the initial condition. So therefore, this is a passive block. That is for this part. Now we know, we can take it as a fact now. Integration is passive. All right, so integration has dynamics inside, but it's a passive system. Let's take a look at this composition of two blocks, integration and the sector. This is called the sector non-linear block. And the graph, in the graph, it looks like this. If this is x, this is h of x, then h of x is going to be guaranteed to lie in this sector. With the two lines, this is 2x, and then the other line is 5x. This is called the sector nonlinearity. And you can see that this sector nonlinearity is passive. I will draw it over here. If we consider, for example, x the product between the input and output, it is going to be equal to x times h of x dt. And we can bound this very easily. Let's see, it is going to be bounded by, lower bounded by x times 2x, right? That is the lower bound of the sector nonlinearity. So it equals 2x squared dt. And this is positive, or at least 0. And if we integrate something that's non-zero, you get non-zero integration. So therefore, this is a lower bound. We actually have something that's nicer than the previous example, right? This lower bound is 0 instead of being a negative number. So sector h of x is passive. Before we move on to talk about the composition, let me ask you guys, if your sector bound looks like this, if let's say h of x is lower bounded by negative 2x, upper bounded by 5 of x, can we still induce passivity of the sector nonlinearity block over here? I will raise this as a question. All right, spend maybe 2 minutes to think about this, whether you can still lower bound the product integration or not. All right. So essentially, I have done some steps. I've laid down some steps over here. Essentially, we want to check whether we can achieve some lower bound that depends only on the initial condition, right? What we can only know from the result is that it's going to be lower bounded by this negative 2x. So it is going to be lower bounded by this negative integration from 0 to t1 2x squared dt. And as t1 increases, we can see that this integration will keep increasing potentially. And there's no way that we can lower bound this one by some term that depends only on the initial condition. So in other words, this is not guaranteed to be passive. Only sector nonlinearities that look like this, all right? The sector is in this region, all right? Positive region are passive. All right? So now we have, this is passive, this is passive. Let's take a look at these two composed together. Let's spend some time on this one. Now, if you have H and integration, what will happen? It's actually the other way around. I integrate first. Then do the sector nonlinearity. So for this one, we know that U integrate becomes X. So X dot is U. And then for here, Y equal to H of X. So when we evaluate, let's say we use the definition, Y and U dt, this is equal to Y is H of X, U is X dot dt. This is just substituting all these into this definition. So it equals H of X dx using the fact in calculus again. And it's going to be H of X times X now using calculus again, is going to be h of x times x minus integration of x dh of x. I will not skip the steps. This is going to be equal to integration from 0 to t1 dh of x times x minus x dh of x. All right. So this is essentially chain rule. This is dh of x times x plus h of x dx, right? So this term is equivalent to this term because of chain rule. So the result is going to be h of x times x 0 t1 minus integration of x dh of x. And h of x is in this sector nonlinearity. We can say something about these two terms again, right? This is ht1, hxt1 times x minus hx0 times x0 and then minus 0 t1. We know that this term we will be able to lower bound or upper bound it, right? This term is going to be at most x times d5 of x. And then it's going to be at least x times d2 of x because of the sector bounds. And both of these terms will be positive, as you can see, right? It has it's going to generate, for example, this one is going to be equivalent to integration from 0 to t1 x 5 dx, and it's equal to 5 half of x squared evaluated between at the two boundaries t1 and 0. All right, and then we know that these will be able to find some bounds for this term, and for these we can also find some bounds too, right? H of x t1, again, apply the sector bounds. We will know that it's going to be lower bounded, right? Lower bounded by, for this case, should be 2x t1 squared. And then this term is going to be lower bounded by the extreme that it can go to in the negative direction is 5 of x0 squared. So you can see that we can have some lower bound. This is always positive, so we can have some lower bound that will appear to look like this. All right. We don't have enough time. I will put the detailed results in Canvas.